The way that we're going to approach chapter 2 is as a class. We're going to spend a whole class session discussing which people or groups of people you think were most interesting in the history of exploring the oceans. What we're going to do in this particular slide presentation is focus on two specific aspects of ocean exploration. First of all, figuring out where we are, and then second of all, accessing the ocean in order to study it. So let's start by talking about how we know where we are. This is a chart reproduced in your book, one of the early charts produced in the Mediterranean Sea area. This is Eratosthenes, who was in Egypt and worked probably through the Library of Alexandria, basically collecting information from traders who were passing through Egypt. So if you look at this chart, people who were traveling the ocean from India and Arabia would come up what we now call the Red Sea, and then they would take a short overland trail to Alexandria, where they could get on ships and go around and do their trading in the Mediterranean Sea, and vice versa. And what the Egyptians did that was very clever was that they asked everybody passing through to share their charts and share the information that they had. If you look at this chart closely, you'll notice that it's got a pretty good depiction of the Mediterranean Sea. It's got a pretty good depiction of the Red Sea, and you can kind of tell where the Persian Gulf is over here. But the farther away you get from Egypt, the worse the details get. So once you leave the Mediterranean Sea, you can see Spain there pretty clearly, the shape of the boot for Italy. But once you get out here and you look at how they've drawn the British Isles, that looks very, very wrong. And if you look up at Scandinavia, they know it's there, but the shapes are wrong. Africa, much too small and misshapen. India kind of pointing in the wrong direction. So there's a lot of mistakes as you get farther away from Egypt. And of course, the reason for that is they would have a lot of good information for things close to home, and the stuff that comes from farther away is more word of mouth and just not very clear. The other issue that they faced was it was very difficult to know where you were. So we'll talk about that in a few minutes, but it turns out it's very easy to figure out, or it's relatively easy to figure out your latitude, or how far north or south of the equator you are. It's much more difficult to figure out your east and west position, which is your longitude. Another method that they show in the book, this is a stick chart from the Polynesians who navigated extensively in the Pacific Ocean. You'll notice this looks nothing like the charts that we're used to. But what they were doing is they were navigating using wave patterns. And so this stick chart turns out to work very, very well. And it shows different wave patterns that you can find around the ocean, and that's how they can find different island chains. So it's a different type of chart, but a very effective chart. This is another very common chart, much more recent. This one is from BC 220. This is from the late 1700s. This was actually made by Benjamin Franklin, showing the Gulf Stream. But what I would call your attention to is kind of how this chart works. If you look around the coast, the shape of the coast is pretty good. Florida looks a little stubby and fat, but the shape is pretty good. And you'll notice that there are lots and lots of labels along the coastline. And essentially what these folks were doing is to navigate the coastline, you would navigate by landmarks or by familiar places. So it could be a settlement, it could be a rocky outcrop feature, it could be a bay. And so those were labeled in great detail along the coastline. And so a navigator would simply have to pay very close attention to what they were going past on the coastline to know where they were. And so that's how this chart works. You'll notice there's not much on the interiors of the continents because, again, it's focused on people who are traveling the ocean, but also this is where the details are. You're kind of following the coastline as you travel. So the big advance comes when we're able to figure out longitude and latitude together to give us a pair of coordinates to tell us exactly where we are. Now, because the Earth is a sphere, we use degrees of arc for our longitude and latitude. So we don't use miles, we use degrees to figure out where we are on the surface of the sphere. The way latitude works is that you measure the angle, if you're in the northern hemisphere, of the North Star above the horizon, and that gives you your latitude. If you are at the North Pole, the North Star is directly over your head, 90 degrees straight up. If you are at 39 degrees, which is where Washington, D.C. is, the North Pole will be 39 degrees above the north horizon, and so that's how you know you're at 39 degrees. If you're at the equator, the North Star will be right on the horizon or at 0 degrees, and so that's how you know you're at the equator. Now, what about during the day? Well, you can do the angle of the sun. You just need to know what day it is because the sun is higher and lower on the horizon based on the day of the year, but still a relatively easy thing to determine. So the way navigators used this was if you knew where you wanted to be in terms of a coastal city, you would take your ship to the appropriate latitude and then go east or west until you hit your target city. And that was called running the latitude. And that was basically how they navigated. The problem, of course, is that you don't know how far away, how many days is it going to take you to get to that city because you don't know the longitude. Longitude, it turns out, is a little bit trickier. We'll discuss this in class as well. But if you watch this ahead of time, you will know the secret. And the secret to longitude is time zones. The farther you go east or west, the more your time zone changes. So for example, here in the Midwest, our time is 1 hour different from the East Coast. Essentially, the sun rises an hour later and sets an hour later. If you go all the way over to the West Coast, they are 2 hours different from us, 3 hours different from the East Coast. So as you move east and west, you can figure out your longitude if you can figure out what time it is back home compared to where you are. And so, for example, if you're from Europe, if you're from Great Britain, if you know what time it is in England, you can tell the local time by looking at the position of the sun. You can compare the time in England to the local sun time and figure out how far east or west of England you are. And that's how you get longitude. Now, the navigators realized this, but the trick was, how do you keep time when you're on board a ship? The best clocks that they had were clocks that operated with pendulums, because you really need to have an accurate timepiece. And of course, in a ship that's rocking back and forth on the ocean, a pendulum doesn't work. And so the government of Great Britain, the king, put out a reward for someone who could develop a chronometer or a timepiece that would keep time very, very accurately. And the story is told in more detail in the book, and you can find even more online about John Harrison's chronometer. But here is an example of one of his chronometers. I can't remember which one this is, but he ultimately won the award for developing this accurate timepiece. This was a very, very precious piece of equipment on board the ship. It was kept by the navigator, and the navigator would use this to compare the local time to the time in Great Britain. And that is also why the prime meridian, or 0 degrees longitude, goes through Greenwich, England, because that is where the Royal Naval Observatory is. And this chronometer was really the first accurate timepiece. So the British got to essentially set 0 degrees longitude through Great Britain. So, and the story is much more interesting and more detailed than that. But that's basically the importance of this clock and why there's a picture of it in your textbook. So to wrap up this discussion, we want to talk just a little bit more about ocean exploration. Scientific exploration of the ocean really began specifically in the 1700s. That's when we really started to see ships setting sail specifically on scientific missions, collecting data and information about the ocean. And this is a cross-section cutaway of one of those early ships. You can see the technology they had was rather limited. If they wanted to measure the depth of the ocean, for example, they had to use a very long rope with a weight on the end, and they would just lower it down until it hit the bottom of the ocean, and that's how they figured out the depth. By the time we get into the 1900s, we start to develop more sophisticated equipment. We're using things like sonar, where we bounce sound waves off the bottom of the ocean and see how long it takes for them to come back up. It's a relatively simple calculation, but that allows us to see the bottom of the ocean. The limitation, of course, is how many times you take the ship back and forth across different parts of the ocean. So the coverage is limited by the number of ships and the number of trips that you can take. We collected an enormous amount of data during World War II because the naval ships going back and forth across the ocean were concerned about submarines, and so they were constantly monitoring what was present beneath the ship. That data was then used to develop ocean charts that showed the shape of the ocean floor. How do we get samples from the ocean floor? Well, this is an example of one of the deep ocean drilling rigs, and it turns out there are only 2 of these on the ocean today. For a long time, there was only one. It was a joint project between basically all the developed countries on the planet, pooled all their resources to develop this ship. This ship and now its companion, there are 2 of them, are constantly at sea, and researchers put together proposals for ship time and to drill 1 or more holes on the ocean floor. And most of the drilling expeditions have multiple researchers looking at each core that comes up for different projects. There's a little narrow blue picture on the right-hand side. This is for scale. It shows you the very, very tiny ship and the long drill stem that they have to hang down to reach the bottom of the ocean floor. And remember, the average depth of the ocean is 2 miles. So the technology involved in making this ship work is really pretty amazing. The ship has to stay in the exact same spot on the ocean 2 miles above the place where it's drilling into the ocean floor. If it moves very much at all, this long strand of drill pipe will break. The other really important aspect of looking at the bottom of the ocean comes from satellites, because using different wavelengths of light, we can actually see through the ocean to the ocean floor. And instead of being limited to the narrow strips that we are with sonar, as the ships go back and forth across the ocean floor, these satellites are able to image much larger areas of the ocean floor and able to do it multiple times. And with different wavelengths of light, they can look at different aspects, not only of the ocean floor, but of the ocean itself. They can look at, use this information to look at patterns of life in the ocean, photosynthesis, energy transmission. And so satellites have really opened up an enormous amount of data collection opportunities for ocean researchers.